So now Albert Valls from IBM is going to talk about a hot topic today in our society. Well, we live under them. So he will talk about artificial intelligence and machine learning solutions from IBM. Okay.
Well, I will talk. Can you hear me in the back? Is it okay? Yep. Okay. So, well, everything in IBM is acronyms, for sure, everything in this world. I will talk a little bit about machine learning, just 3 slides, but I was asked to focus on our parallel file system, which is HDFS, now renamed to Spectrum Scale. And to begin with, I will start with some slides of strategy about high-performance computing and how this is evolving to high-performance data analytics. So there is an intersection between the big data world and the traditional HPC, and we found this to be HPDA. Okay. So what we've seen is that the market is changing. There are new drivers, new directions that influence our strategy in terms of what we offer to the market for HPC. We see the increasing volumes of data exploding, especially the non-structured data. We see that we need to get insights from this data, and this is let's say, some sort of traditional problem in scientific calculations. And, but we need to take care of different steps. In a process, in a supercomputing process, we have to take care of different steps on what we call a workflow. Okay? And many of these analytical steps can take advantage now of in-memory processing. There is always the problem of energy efficiency. This is typical in HPC, and we still have to deal with this. And what the picture in the bottom right shows you is that we cannot keep up with Moore's law if we only rely on CMOS technology. So we must take advantage of others to develop in order to increase this performance that we expect from Moore's law. And this is the last sentence here. So making accelerators consumable. And accelerators of 2 different types. We will see later. So in terms of strategy, what IBM did something like 3 years ago is opening the specifications of their power processor. By the way, this is also an acronym. Anyone not from IBM knows what power stands for? No? It's performance optimization with enhanced risk. So this means our power processors are RISC processors, as per comparison against the x86 FISC architectures. And this is the processor we put in our big systems, in our Unix machines, and also Linux on power. What we did 3 years ago is opening the specifications for this architecture, the power architecture, and we started this journey about Open Power Foundation. At the beginning, we were only 5, but you can see there are some of the players which are quite important: Google, NVIDIA, Mellanox, Tile. In 3 years, we have expanded the ecosystems to, there it says 200, but the last news, it's about 300 different companies working on the Open Power Foundation. By the way, we've got 2, 3 universities in Spain already adhered to this open power strategy. And what we achieve by this is providing new systems which take advantage of these different partners in the ecosystem. For instance, the last system that we released something like 4 months ago, something like this, it's a 2U system with 2 power processors, and then we can fit there 4 NVIDIA GPUs. This in a 2U space. Okay, if you focus only on teraflops, then 21 teraflops. It's quite a best. But as I told you, we shouldn't only focus on this peak performance. We must take advantage and make the GPUs consumable, which means it should be easy to port applications and for the applications to take advantage of such GPUs. But this is an example of well, different players putting technology together, okay, and providing a product to the market. So why the power processor? The power processor, well, it's now in its 8th generation. After the summer, probably we will be announcing Power 9. Power 9, we'll announce Power 9, but there won't be any availability of servers running Power 9 till beginning of next year. And the reason behind is because the production is sold out. I mean, we have to provide Google with lots of Power 9, and we have to provide also Lawrence Livermore and Oak Ridge with a very big system, which requires something like 6,000 nodes. On the Power 8 side, what we focused was not on increasing number of cores in the chip, but on providing big cores and providing a good hierarchy in the cache structures, so that these cores are not waiting idle for the data to come. Okay? So we can run up to 8 threads in every single core, per comparison against Intel with Hyper-3, which is 2. We've got bigger caches. We'll talk about accelerator debuggings. And we've got, well, more memory bandwidth. This is also an obsession, I would say, in the processor design, so as to keep the cores with enough data to process.
Excuse me.
Yeah?
Could you please go back? So
Sure.
1 terabyte per socket is the memory bandwidth?
No. That's the maximum amount of memory you can address in one socket,
Okay.
1 tera or 2 tera. It depends on whether you are, no. Memory bandwidth, aggregated memory bandwidth, it's 230 gigabytes per second, which is something like 3 times what we can achieve in an Intel box, which is now at 96, as far as I remember. Okay, so 1 terabyte is memory capacity, not memory bandwidth. Okay, and depending if we are talking about the small boxes, this is 1 memory controller per chip, then it's 1 terabyte. Yeah, exactly. That is 1 terabyte. If you're talking about the big scale-up machines, then you can address 2 terabytes per socket, grow up to 32 terabyte system. But this is more devoted to, for instance, SAP HANA or other kind of workloads. Okay? So in terms of acceleration, we've got different types of acceleration. With the Minsky, this box with Power 8 and special links, what we delivered to the market is a new way to attach the GPUs, the NVIDIA GPUs. In fact, this is something that we developed together with NVIDIA. And we are not constrained by the bandwidth of the PCIe Gen 3 bus. So instead of limiting the GPU to CPU bus to 16 gigabytes per second, we can grow up to 80 because it's a 40 full duplex. Okay? And the other way of providing acceleration is by this CAPI. So it's Coherent Accelerator Protocol Interface. Well, another acronym for sure. What this means is we can attach I/O adapters that talk directly to the processor with an streamlined protocol. And instead of having to deliver 10,000 operations to do I/O, we can reduce it magnitude, an order of magnitude. So instead of 10,000, 1,000, something like this. What we achieve by this is accessing flash, for instance, with CAPI-enabled adapters in a very, very low latency and high IOPS. Okay.
Do you have a case where we're using CAPI and we get some results? Can we compare using CAPI without CAPI?
Not here, but for instance, for Redis Lab, we've got a benchmark which compares attaching or not attaching with KP-enabled I/O adapters. And we did with a single two-socket system, power system, the same work as 24 Intel boxes, dual-socket boxes. Okay? I can show you later. So we've got a clear roadmap. Right now we are at the Witherspoon. I don't know. No, not here either. So right now we are at the Minsky. By the end of this summer, we'll have Witherspoon, which is Power 9. And what you can see is we've got a clear roadmap and aligned with NVIDIA. NVIDIA, in fact, has already announced its Volta CPUs. We will be delivering these in Power 9 boxes after the summer. And we'll have additional interconnect technology at the next release of InfiniBand HDR. It makes not much sense to put HDR right now in a PCI Gen 3 slot because you are limited by the slot right now. Yeah, that's it. Well, there is roadmap up to Power 10, 2020 and beyond. Okay. So as I told you before, the flops are not the only K performance indicator. Okay, in HPC, we have to take into account the different steps in a workflow. This is an example for seismic processing, but there is the same issue, for instance, in genomics, what they call the pipelines. Executing pipelines means having different processes that with interdependencies and with very specific requirements in every single step. So what you need to have is a balanced system design. And what we are observing right now is that there is this confluence of big data or analytics workloads with the more traditional HPC workloads. And there is a common challenge in this part in the middle about I/O performance, scalability, and new technologies regarding storage. So storage, it's seen as a capital topic within HPC. For that, probably you know this product. In other words, it's GPFS, Global Parallel File System. Now, this has been changed to IBM Spectrum Scale. Everything that can be software-defined storage, it's renamed within the name of Spectrum, within the Spectrum family. What we've got in this product is, well, the capability of storing files, for sure, objects, and we can deliver also integrated analytics because we've got that HDFS connector. It's a single namespace, POSIX compliant, and we can work with different pools and different categories of storage infrastructure below. We can work with flash systems, with traditional disk systems, high capacity disk for archiving, even tape within the same file system. Okay. And well, it's been a long way since GPFS was initially released, probably more than 20 years. And we are right now at release 4.2.2. Well, I'm not expecting you to read this, just for you to have a glimpse on the long time we've been working with GPFS. Anyone of you has played with GPFS, has GPFS? Yeah? So you probably know this. The origin of GPFS is in the broadcast multimedia systems. The digital broadcasters had to edit their video files and had to provide voiceover. The editors were working in parallel against a very same file, a very big file. And this is why all the commands in GPFS, if you have to do it in CLI, start with whatever, because it's multimedia file system originally. Then what IBM saw is that this specific use of multimedia was applicable to HPC too. And what we are seeing now, it's also applicable to the big data analytics world. Okay? So it's a parallel file system. We've got what we call the NSD, network shared disks, and we can have NSD servers, which have storage attached, or NSD clients, which are HDFS clients, which access the file system through the network. This can be either 10 gig, 40 gig, infinite. Okay? The beauty of the system is that it spreads the file among all the servers, and well, we can have an easy scale and in terms of capacity and in terms of performance. The file system is spread evenly across all the servers. We can have direct clients. This is what we call the application nodes that directly mount the file system through the network. We've got spectrum scale servers, which are the servers that have storage attached. This can be any kind of storage. And we can export these HDFS to other protocols by means of protocol nodes. This is NFS, thieves, and also right now with Swift, OpenStack Swift, so object storage. Special feature is about scalability. Scalability in terms of data and in terms of metadata. Every single node in a HDFS cluster can be either data server, metadata server, or both. And well, this is the details about how do we provide scalability. People say it's God is in the details. So these specific things and very detailed things are what make HDFS really scalable and performant. But people also say evil is in the details. So, well, it could be some complex. But for sure, this capability of being able to split metadata servers, data servers, and lots of features there enable the file system to be really scalable and really performant. The last release have incorporated GUI. This is something that was required for a long time, but, well, it depends. With a command line, you can do everything. But GUI, it's, well, more user-friendly, and it can be integrated also in the spectrum control management stuff. Okay. We've got also built-in tiering. This is a special feature within HDFS that allows you to automate how do you place the files within the file system. You apply policies, and this affects either the initial placement or the automation to move data which is not really frequently accessed to more cost-efficient tiers. Okay? Initially, we worked with Flash, high throughput disk, high capacity disk, and now we can even integrate within the ILM structure either tape by means of a spectrum archive. This is the renaming of, probably you've heard about LTFS, linear tape file system. So putting data in an LTO drive as if it was a hard drive. Okay? You can have a tier either in tape, which is the most cost-effective way of storing data, or offloading to a cloud provider. Right now, we are working with Supplier for sure, which is our cloud way, or cloud object storage. And I think in the next release will be available for Amazon S3. Okay? The good point is that the user, the end user, doesn't see any change. I mean, he accesses his file, he sees the file system, he sees a tab in the file system. Even that the data is migrated to tape or to cloud object storage, he still sees the file within the file system. So transparent to the user. The other feature about mixing analytics and HPC is HDFS transparency. Well, this what the colleague of Intel told about Lustre also. Instead of having to move data between my compute nodes or my ingestion and the processing in Hadoop clusters, what we can work is directly with MapReduce and codec stores to the Spectrum scale file system. The use case, for instance, for this is instead of having to build a Hadoop cluster with a certain amount of nodes in order to have enough capacity and performance, you can start with a low number of nodes because the storage will provide the performance. Okay? We can do compression for sure. I won't extend on this. We do encryption, and it's not really impacting on performance, well, less than 5%, which is quite good. And, well, going into the details, performance feature, the local read-only cache, that means that cache is done at the GPFS client level. This is why it makes not sense to put a lot of memory in GPFS servers, because cache is done at the client level. Or we can do high available write cache. This means grouping the small writes in large chunks to optimize the writing, but ensuring the reliability. So this means that GPFS client, when has a lot of small writes, caches this and copies this to another client, and then flashes or destages the local cache to the central file system. Okay? We can have multi-cluster capability, which means that a cluster in one side can access and mount the data in another side. And this is something used, for instance, in DESA project in Europe, okay? Or at least it was used. And we've got synchronous copy if you've got different failure groups within your storage. Okay, so the GPFS client writes synchronously to two sides, and then it reads from the fastest one. If the distance between sides is too much, then writing synchronously it's difficult, and we have to have a different capability, which is replicating asynchronous between different sites. This is what provides the capability active file management. Okay? So that means that different institutions having GPFS can replicate data between them, and we are talking about long distance, so even through one connectivity. There is a home directory where, well, not directory, but file system where the information lives, and then there is a cache, and there can be different deployment ways. The remote cache can be read-only, or the remote cache can be single writer. That means you can centralize in one point all the different changes that are in the different sites, and have a central point to do, for instance, a centralized backup. Or you can have local update deployment. For instance, you get a release of software, whatever it is, you install it locally, and you do updates locally, but you don't want this to be replicated to the original home site. Or it can be multiple independent writers. A special implementation of Spectrum Scale in an appliance way, it's what we call the elastic storage server. What this means is that we do not need the traditional storage controllers, because the write operations are done on the servers. And the servers control well, the GBOT expansions, just a bunch of disks. And they create the clustered RAID, and they manage all the things within these disk expansion enclosures. Okay. The advantage of a spectrum scale, the clustered RAID thing is that, well, you can provide different kind of RAIDs, but the main value for sure is about faster rebuilds and minimal impact of rebuild on system performance. We'll have a look at this especially. So this is really important when we are talking about high capacity drives. Right now we are talking about 8 terabytes, 10 terabytes, and 12 in a near future. When you lose one of these drives and have to reconstruct these, it can take even days, I would say. So it's important to focus on this fast rebuild feature. Okay. The types of RAID that you can implement at GPFS level are these ones, the 8+2, 8+3, or 3-way replication, 4-way replication. Typical use is for data, we use the RAID6 with 2, 3 parities, or for metadata, we can provide more security and do this 3-way, 4-way replication. This is graphically what the clustered RAID means in terms of rebuilding performance. We've got here typical RAID with hot spare, and what this filing, this means only one disk, the spare is rebuilding. And if you've got a declustered RAID with stripping, and all the disks are contributing to the rebuilding. So we can reduce the rebuild time by 3.5 times. Or the typical declustered RAID6. So here you've got 3 different RAID6 with hot spares, or the declustered RAID graphic. What this means, if you have 2 filed drives in this scenario, you would have a RAID6 in critical state. Instead, if you're working with the clustered RAID, only one of the stripes is affected by 2 faults. So having to recover this, well, you can see this a little bit. During the critical rebuild, there is an impact on performance, but this rebuilding of the stripe affected with 2 faults, it's really fast. We are talking about minutes. Once we are in a non-shot critical state, then the performance, it's again good performance. So this is managed by what we say the data integrity manager. This is the piece that prioritizes tasks within GPFS, which is more priority to the rebuilding critical state LUNs, and then rebalance and data screwing goes behind. We've got end-to-end checksum, not only on the drives, but the chunks that we transfer over the network. So this allows us to repair soft and read errors or lost missing writes. And this is the kind of systems that we can deliver. We've got 2 servers, and depending on the kind of expansion, we've got different models with different capacity and different performance. The topmost capacity is in a single rack. You can fit something like 2 petabytes, and you can obtain 25 gigabytes per second. This depends on the kind of interconnect you use in your ESS. And there are new models with even a higher capacity expansion. In 5 use, we can fit 90 drives, and this allows us to provide more capacity, more performance. These are building blocks. I mean, you can put it one beside the other and create a single file system with more performance, with more aggregate performance. So the way we choose usually which kind of ESS it's, does it fit in a certain case, it's well, taking into account how much capacity do I want and how much throughput do I want. Okay. And just some few words, I think I'm on time, yeah. We've got another interesting piece, which is the kind of schedulers we inherited from the acquisition of platform computing. This is the typical LSF, job scheduling stuff, load sharing facility. What this does is, well, this is graphically what it does. I mean, it builds the Tetris so that you can get faster results or you can use fewer resources. This has been extended not only to HPC workloads, but also to analytical workloads. We've got connectors to launch Hadoop tasks or even Spark right now. And well, just the 3 slides about artificial intelligence. Well, everybody's talking about artificial intelligence right now, but this has been, I think, in the market for quite a while. In fact, the other day I saw in the news it was 20 years from the Deep Blue, the one that the system that played chess against Kasparov. So this was an initial thing of machine learning. We've got machine learning also in our lives. Every one of us, for sure, has an anti-spam configuration in their mail boxes. And what we are talking right now about deep learning, it's the use of probably the convolutional neural networks to solve problems that seem to be unforeseeable. So the typical application of machine learning right now is to do image recognition or to do fraud detection or to do pattern matching. But there are lots and lots of different codes. And that's the problem that IBM detected. So what we try to solve with Power AI is to bring together the different frameworks, Café, Torque, Theano. TensorFlow is there, but not being shown. And put all these things together so that you can set up a machine learning environment really, really fast over a set of these Minsky node power systems with NVIDIA's. Some of the libraries take advantage of NVIDIA acceleration, others not, and put it either in a spectrum scale or in the cloud. And where can we start? It's as simple as a single node with some GPU and some memory, and then deploy this Power AI. By the way, you can download this free, and well, we can have really good numbers in really cost-effective, I would say, infrastructure. Starting at 27, it's not really really expensive. And that's all from my side. Any question or we discuss later? I'll be around. So. Go on. One question.
So on GPFS part, you mentioned tokens, and which is during our evaluation of GPFS, one of the problems we faced, it was scaling with the number of tokens. You know, if you have a number of servers, you will be limiting the bandwidth or the access to data because of the tokens. Every server need to authenticate the tokens so the client could use it. So that was a problem, and one of the ways is to add the number of servers, so you will have parallel servers that deliver tokens. But that brought us to another problem. I'm a customer, so I have now to pay a multiple license of servers to be able to scale the performance. Yeah. So
well, this has changed a little bit in the latest release. We can either license by the servers, the number of sockets in the servers, or we've got right now data management licensing. which means you license capacity, and then you can deploy any number of servers, any number of protocol nodes, any number of clients.
Okay.
So licensing by capacity. Any other question? No? Thank you.
Okay, thank you.